I am Ms.R.RUBASHRI, Assistant Professor of Physics, A.D.M. College for Women, Autonomous, NAGAPATTINAM. Let's see about my topic is Semiconductor Physics and Optoelectronic Devices. What is semiconductor? Semiconductor are material which have a conductivity between conductors and the non-conductors or insulators. Semiconductor can be compounds such as gallium arsenide or pure electrons and elements such as germanium or silicon. Physics explains the theories, properties and mathematical approach related to semiconductor. Example of semiconductors: gallium arsenide, germanium and silicon are some of the most commonly used to semiconductors. Silicon is used to electronically circuit fabrication and gallium arsenide is used in solar cells, laser diodes, etc. Tables and contents of semiconductors: holes and electrons, band theory, properties of semiconductor, types of semiconductor, intrinsic semiconductor, extrinsic semiconductor, N-type and P-type semiconductor and its application. Holes and electrons in semiconductors. In type of charge carries the flow of current semiconductors. Holes valence electrons are the positively charged electric charge carried. The electrons are the negatively charged particles. Both electrons and holes are equal in magnitude but opposite in polarity. Electrons and holes is the mobility. In a semiconductor, the mobility of electrons is higher than of the holes. It mainly becomes the different band structures and scattering mechanics. Electrons travel in a conduction band, whereas holes travel in valence band. When an electric field is applied to holes, cannot move as freely as electrons due to the restrict moments. The evolution of electrons from the inner shell to higher shell results in the creation of holes in semiconductors. Since the holes experience to stronger atomic force by the nucleus than electrons. Then holes in lower mobility. The mobility particle is semiconductor is effectively particle as the lesser. The time between scattering event is more. For intrinsic silicon, 300 K and mobility of the electron is 1500. The bond model of the electron in silicon of valence 4 is the one of the free electrons blue dots and the leave lattice position is the holes are gray dots. This one is the picture. Band theory of semiconductor. Introduced the band theory happened during the quantum revolution in science. Walter Hilter and they discovered the energy band. We know that the electrons in an atom are present at different energy levels. When we try to assemble a lattice of the solid with n atoms, each level of an atom must split into n levels in the solid. This splitting of short and tightly packed energy levels from the energy band. The gap between adjacent band representing a range of energies that possess no electron in is called band gap. This one is the band gap in the materials. First one band gap, conduction band and then valence band. This insulators, semiconductors and the conductor metals. First one is valence band. The energy band involving the energy level of valence electron is known as the valence band. It is the highest occupied energy band. When compared with the insulators, the band gap in the semiconductor is smaller. It allows the electrons in the valence band to jump into the conduction band or receiving any external energy. Next one is conduction band. It is the lowest band that includes the energy level of positive. It denotes the holes or negative with the electrons. It is the conducting electron resulting the flow of current. The conduction band possesses a high energy level and the generally empty. The conduction band is semiconductor accepts the electron from the valence band. What is the Fermi level in semiconductor? The Fermi level denoted by EF is present between the valence and conduction band. It is the highest occupied molecule orbital at absolute zero. The charge carriers in this state have their own quantum state and generally do not interact with each other. When the temperature rises above absolute zero, These charge carriers will be being to occupy straight above the Fermi level. In p-type semiconductor, there is an increases in the density of unfilled state, thus accommodating more electrons at the lower energy level. And then n-type semiconductor, the density of state increases, therefore accommodating more electrons in the higher energy level. Properties of semiconductors. Semiconductors can conduct electricity under some preferable condition or circumstance. Unlike conductors, the charge carrier in semiconductor arise only because of the external energy. It causes a certain number of valence electrons to cross the energy gap and jump into the conduction band, leaving an equal amount of the accompanied energy state into holes. The conduction due to the electrons and holes is equally important. Resistivity 10 power minus to 10 power 6. Conductivity 10 power 5 to 10 power minus 6. Temperature coefficient of resistance is negative. And then current flow due to the electrons and holes. Some important properties of semiconductor. Semiconductor act like insulators and 0 Kelvin. On increasing the temperature, they work as conductors. Due to their exponential electrical properties, semiconductors can be modified by doping to make semiconductor devices and from energy conversion switches and amplifiers. Lesser power losses, and then semiconductors are smaller in size and possess less weight. The resistivity is higher than insulators or conductors but lesser than insulators. The resistance of semiconductor material decreases with an increases in temperature and then vice versa. Then types of semiconductor. Two types of semiconductor, intrinsic semiconductor and extrinsic semiconductor. This one is the picture. Intrinsic semiconductor in type of the material is made to be very pure chemically. It has the single type of element. And then germanium and silicon are the most common type of the intrinsic semiconductor elements. They have 4 valence electrons. They are bound to the atom by a covalent bond and absolutely 0 temperature. When the temperature rises due to collisions, few electrons are unbounded and become free to move through the lattice, thus creating an absence of original position of the holes. The free electrons and holes contribute to conduction of electricity in the semiconductor. The negative and positive charge carriers are equal in number. The thermal energy is capable of ionizing a few atoms in the lattice and hence there is the conductivity is less. Energy band diagram in the intrinsic semiconductor. In intrinsic semiconductor, current flow due to motions of free electrons as well as holes. The total current is the sum of electrons current IE due to the thermally generated electrons and hole current IH. Total current I is equal to IC plus IH for intrinsic semiconductor finite temperature and the electrons is exit to the conduction band. It decreases and increases in the band gap, where Eg is equal to energy band gap, Hb Boltzmann constant. Extrinsic semiconductor. The conductivity of semiconductor can be generally improved by introducing a small number of suitable replacement atoms are called impurity. The process of adding impurity atom to pure semiconductor is called doping. This two types, N-type and P-type. N-type semiconductor is mainly due to electrons, majority minus electrons and minority into holes. When a pure semiconductor is doped in pentavalent impurities, then 4 electrons out of 5 valence electrons bond. With the 4 electrons are germanium or silicon. The 5th electron of the dopant is set free. That impurity atoms donate the free electron for conduction in the lattice and is called the donor. Since the number of free electrons increases with the addition of impurity, the negative charge carries increases, hence it is called the N-type semiconductor. Crystal or hole in the neutral, but the donor atoms becomes as the immobile positive ion. The conduction is due to the large number of free electrons, the electron in the n-type semiconductor, and the majority carrier and the holes of a minority carrier. P-type semiconductor, mainly due to the holes, entirely neutral, I is equal to IH, and majority holes in the electrons. When a pure semiconductor is doped with a trivalent impurity, then the 3 valence electrons of the impurity electrons in semiconductor, this leaves an absence of electrons in the impurity, which is called the acceptors. With an increase in the number of impurities, holes, the positive charge carriers are increased. Hence, it is called the p-type semiconductor. Crystal as a whole is neutral, but the acceptor becomes an immobile negative ion. The application of semiconductor, that low cost and controlled conduction of electricity may ideal to be used in the various purposes in wide range component and devices, transistor, diode, photosensor, microcontroller, integrated chip, and much more are made by of semiconductor. Uses of semiconductor in everyday life. Temperature sensors are made with semiconductor devices. There are used in 3D printing machines. Uses in microchips and self-driving cars. Used in calculators, solar plates, computers, and other electronic devices. Transistor or MOSFET used on a switch in the electrical circuit and manufactured using semiconductor. Industrial uses of semiconductor. The physical and chemical properties of semiconductor make them capable of designing technological wonders like mobile microchips, transistors, LED, solar cell, etc. The microprocessor used for controlling the operation of space vehicles, trains, robots, etc. is made up of the transistor and other controlling devices which are manufactured by semiconductor material. Importance of semiconductor. They are highly portable due to their small size. They require less input power. Semiconductor devices are shockproof. They have a longer lifespan. And then there are noise free while operating. Difference between conductors, semiconductors, and insulators. First one, parameters. And then conductor, a material allowed to electric current to pass through in very easily. Then semiconductor, in between conductors and the insulators. Then insulator is material, do not allow the electric current to pass through them. Parameters, forbidden gap, energy gap. Conductors, no energy gap, the conduction band overlap the valence band. Semiconductor is small energy gap, and then insulator is very large energy gap. Then parameter, conduction. Conductors due to free electrons. Semiconductor due to movement of both electrons, positive and negative of the whole carrier charges. Insulator is no conduction. Then resistivity parameter. Conductor is low of the order. Then semiconductor intermediate from the meter to 10 power 5 meter. Insulator is very high of the order. Parameter, temperature coefficient of resistivity. Conductor is positive, semiconductor and insulator is negative. Parameter, valence electrons in outermost shell. Conductors less than 4, semiconductor 4, insulator more than 4. For example, conductors, metal like silver, gold, copper, aluminum, etc. Semiconductor, silicon, germanium, gallium, arsenide, etc. And then insulator, air, mica, glass, paper, polythene and wood, etc. Next one, PN junction. PN junction is the interface of a boundary between two semiconductor material types, namely P-type and the N-type. Inside a semiconductor, in the semiconductor of the PN junction is created by the method of doping. The P side or positive side of the semiconductor has an excess of holes and the N side or negative side has an excess of electrons. This process of doping is explained further details in the next session. This one is anode and cathode. Anode is the positive charge, cathode is the negative charge. Formation of p-n junction. P-n junction, there will be a grain boundary that would inhibit the movement of electrons from one side to another side by scattering of the electrons and holes is used to the process of the doping. Let us consider a thin p-type silicon semiconductor sheet. If we add a small amount of pentavalent impurity to this, a part of p-type silicon will get converted to the n-type silicon. There is a difference in the concentration of holes and the electrons at the two sides of the junction. The holes from the p side and the n side is the electrons. From the n side diffuse to the p side. These give rise to the diffusion current across the junction. Bias is conditioned for the p-n junction diode. Zero bias, forward bias and reverse bias. There are the three biasing conditions. Zero bias is no external voltage is applied to the p-n junction diode. Forward bias is the positive terminal of the voltage potential is connected to p-type while the negative terminal is connected to n-type. Reverse bias is negative terminal of the voltage potential is connected to the p-type and the positive in the connected to the n-type. Forward bias of the p-n junction, this one is the picture. When the p-type is connected, battery positive terminal and the n-type is crystal negative type terminal. Then the p-n junction is the forward bias. When the p-type junction is forward and built-in electrical field, p-n junction applied electric field are the opposite direction. When both the electric field up adds the resultant electric field in the magnitude lesser of the electric field. This result is less resistive and thinner deflection region. The deflection region is resistance becomes negligible when the applied voltage is large. In silicon and the voltage of 0.6 voltage, the resistance of the deflection region becomes completely negligible and the current flow across in the impedance. Reverse bias connection, this one is the picture. When p-type is connected to battery negative terminal and the deflection region and then resistivity. In case of built-in electric field applied in same direction, when two fields are added, result an electric field in same direction but built electrical field in the thicker deflection region. Then Zener diode. What is the Zener diode? In highly doped semiconductor devices, specially designed to function in the reverse direction, it is the engineering to wide range of the Zener voltage and certain types of the even adjustable achieve variable voltage regulation. The symbol used to represent a Zener diode is circuit diagram is the similar to regular diode but with a unique addition. It consists of the triangle or pointing towards the cathode side. This triangle is accompanied but by two perpendicular lines at the cathode end, one extending upwards and the other ending extending downwards. These lines indicated the specific behavior of the Zener diode and help distinguish it from other type of the diodes in circuit diagram. The symbol provides a visual representation that allows engineers and technicians to easily identify and understand the presence of Zener diode in a circuit. VI characteristic of Zener diode in forward action and reverse action. Then Zener breakdown voltage. The VI characteristic of a Zener diode can be divided into two parts, forward character, other one is reverse character. Forward characteristic of Zener diode, the first graph is represent the forward characteristic of Zener diode. From the graph, understand it is almost identically to forward character of the p-n junction diode. Reverse characteristic of Zener diode is applied to the Zener voltage, a small reverse saturation current I/O flow across the diode. This current is due to thermally generated minority carriers. Zener breakdown voltage. The Zener or reverse breakdown voltage range from 2.4 voltage to 200 voltage. Sometimes can 1 maximum of the surface in the devices. Then current, it is the maximum current at rated Zener voltage. Then current, it is the minimum value of the current required for the diode to break down. Temperature stability. Diodes around 5 voltage has the best stability. Zener resistance, it is the resistance to the Zener diode exhibit. Then photodiode. What is the photodiode? A photodiode is one type of light detector used to convert the light into current or voltage based on the mode of operation of the devices. It comprises optical filter built-in lenses and also surface areas. These diodes have a slow response in time when the surface area of the photodiode increases. Photodiode are like regular semiconductor diodes, but that they either visible light reaches in the photodiode. Then pin junction diode of the PN junction. Some photodiodes will look like light emitting diode. They have two terminals coming from the end. The smaller end of the diode is cathode terminal, while the longer end of the diode in the anode terminal. Under the forward bias condition, the conventional current will flow from anode to the cathode following the arrow in the diode symbol. Photocurrent flow in the reverse direction in the direction of the photodiodes or class of the diodes that convert light energy to electricity. Their working is exactly the opposite LED, which are also diodes, but they convert electricity to light energy. This one is the photodiode picture. Then cathode and anode. Photodiode working. Photodiode is subjected to photons in the form of light, which affect the generation of electron-hole pair if the energy of the falling photons in the greater than the energy gap Eg of the semiconductor material. The electron-hole pair created are separated from each other before the recoupling due to electric field of the junction. The moreover of the electromotive force created, the greater of the current flow, the magnitude of the electromotive force created depends directly upon the intensity of the incident light. This effect is the proportional change in the photocurrent with the change in light intensity can be easily observed by the applying reverse bias. Since photodiodes generally current flow directly depends upon the light intensity received, they can be used as a photodetector to detect optical signals. Built in lenses and optical fibers may be used to enhance the power and productivity of a photodiode. Applications of photodiode. Photodiode are used in a simple day-to-day life and then application. Photodiode are used in the solar cell panels and then logic circuits and then reduction circuits or character recognized circuits and then used to exact measurement of the intensity of light in science and industry. Photodiode are faster and more complex and then normal PN junction diode and hence are frequently used to lighting, regulation and optical communication. Types of photodiode, then two types, PN photodiode, then Schottky photodiode. There are numerous types of photodiode available in market and then all work of the same basic principles. Some include other effects. The working of the different types of photodiode in the types and classified to the functions. PN junction photodiode is the pin junction photodiode or first form of the photodiode in widely diodes of the before the development of pin junction. This one is the P and N type, positive and negative symbol. This photons is the P type and N type deflection layer of the PN junction photodiode. Then pin photodiode. Pin photodiode are developed by PN junction photodiode. The operation PIN photodiode, similar to the PN junction. Then PIN photodiode manufactured differently to improve the performance. The developed and increases the minority carriers current and response speed. Then last one, Schottky diode. In a normal PN junction diode, a P-type semiconductor and N-type semiconductor are used to PN junction. When P-type semiconductor is jointly with an N-type semiconductor and junction is formed between P-type and N-type semiconductor. This junction is called as PN junction. In Schottky diode, metals such as aluminum or platinum replace the PN junction or semiconductor. The Schottky diode is named after German physicist Walter. This one is Schottky diode. Schottky diode is also known as Schottky barrier diode, surface barrier diode, majority carrier devices, hot electron diode or hot carrier diode. Schottky diode are widely radio frequency RF application when aluminum or platinum metal is joined with N-type semiconductor. A junction is formed between the metal and the N-type semiconductor. This junction is known as the metal semiconductor junctions or MS junction, and then metal semiconductor junction formed between metal and the N-type semiconductor create a barrier or deflection layer known as the Schottky barrier. This one is the picture of Schottky barrier. Thank you for this watching.